Professor Haotian Wang. Professor Haotian Wang is currently William Marsh Rice Trustee Chair Assistant Professor in the Department of Chemical and Biomolecular Engineering at Rice University. He obtained his PhD degree in the Department of Applied Physics at Stanford University in 2016, and his Bachelor of Science in Physics at the University of Science and Technology of China in 2011. In 2016, he received the Loran Fellowship and began his independent research career at Harvard as a principal investigator. He was awarded a 2021 Sloan Fellow, the 2020 Parker Fellow, 2019 CIFAR Azure Global Scholar, and Forbes 13 under 13, highly cited researcher, etc. He serves as the editorial board of communications materials. His research group has been focused on developing novel materials for energy and environmental applications, including energy storage, chemical fuel generation, water treatment. So now let's welcome Professor Haotian Wang.
Oh, thank you. Thank you, Haitao, for your nice introduction and your kind invitation to have this great opportunity for me to share with the audience some of our past few years research, especially on the electrochemical carbon dioxide conversion to fuels and chemicals. So let me first start with send my congratulations, of course, to the 85th anniversary of PolyU, which is a fantastic journey over the past 85 years. And me between PolyU has recently been connected by one of my group of alumni, Dr. Xiao Zhang, who worked as a postdoc in my group for the past 2 years and recently joined PolyU in the Department of Mechanical Engineering. He has been doing very well in my group, and I'm pretty sure that he will doing even better on the nutritious ground of Poly University. So let's come back to the research topic. I think, just now Professor Chenjing Wang has introduced fantastically about the background, the importance of CO2 reduction. So there is no need for me to, redo that again. So let me just put that in another perspective from the development of clean technology that we know the clean electricity harvest from solar or wind. The technology has become more and more mature as we know that the price, the electricity cost coming from solar panels continue to decrease over the past few decades or so. As we know that there was ambitious US DOE's goal of bring down the electricity price of solar power, electricity price to 3 cents per kilowatt hour. And this sunshot goal was recently even brought down to 2 cents per kilowatt hour. So that can be easily compete with the existing fossil fuel electricity cost. So what does that mean? This is not only a meaningful competition with fossil fuel traditional electricity productions, but it actually could bring us a revolutionary change to the clean tech. Especially now we can expect there will be a lot of abundant, at the same time it's green and also cheap electrons in the next few decades or so. So how we are going to make use those electrons, it will become opportunity, but at the same time it's a challenge. So of course, in electrochemical perspectives, we want to combine those electrons with simple molecules that we can access from atmospheres like CO2, oxygen, nitrogen, water, and so on. And with the help of electrocatalysts, we can accelerate the chemical transformations and store those electric energies into simple chemical bonds, like CC bonds doing CO2 reduction to hydrocarbons, HH bond doing water splitting and generate clean hydrogen, or NH bond if you do nitrate or nitrogen reduction to ammonia. So that will help us to fulfill a lot of the, to fulfill a lot of these applications in energy storage, as well as a green and sustainable pathway towards chemicals and fundamental chemicals and fuels. So among those electrochemical processes, as we know that CO2 reduction has become one of the hottest and most important research area in the past 1 or 2 decades, not only because it has significant impact on the climate change, but also its intrinsic interests in the scientific advancement is very important. That can be also seen from these half-cell reactions. You can see that CO2 coupling with electrons, with protons from water, that can generate a wide range of products, ranging from C1 to C2 to even C3 products. So there are so many pathways that is existing in this electrochemical reaction. That's the reason why there are so many studies ongoing to understand mechanisms to promote the performance towards a single product, and also for device engineering for commercialization and so on. So among those C1 to C3 products, the field has also did some of the simple techno-economic analysis and shows very promising results. As you can see from this, the blue bar actually represent the product that is coming from the traditional chemical engineering process with the cost that is coming from, that is the market price. Because we know that those chemical commodities has very narrow profit margin. So usually that market price can generally represent a large scale of these production cost. And if you produce the exactly the same type of chemicals, not from traditional chemical engineering, but from electrochemistry, from the electricity, because of the lower and lower cost of electricity, you can expect very competitive cost coming from electrochemical process, especially for carbon monoxide and formic acid. These 2 products here is because these are the most easiest achievable product coming from CO2, only 2 electron transfers, and it has the best performance compared to other products. You know, the higher value products, you have lower and lower performance and the selectivity. But there are still a lot of requirements actually buried underneath this techno-economic analysis. If there are a lot of things that we need to meet with so that we can deliver these attractive targets. The first of all, we have to bring up the current density, so which is the geometric current per areas of the electrode to produce the chemicals. The higher current density, of course, the smaller size of your reactor, the device that you will need to have. So the capital investment, the capital cost will be lower. So generally speaking, you have to be more than 100 milliamp per centimeter square to make economic sense. But you know, in commercial water splitting, water electrolyzers, this requirement could be 1 amp to 3 amp per centimeter square. So this is a very minimal requirements for CO2 reduction. Under that high current densities, you have to guide the electrons towards one single product. Of course, if you produce, like Professor Chen Jingguang just mentioned, if we just tune the ratio of hydrogen and CO to feed specifically to Fischer-Tropsch reactions, that is different. So what I mean here, the selectivity is the electron selectivity. So the electrons that goes to the desired product has to be more than 90% or at least 80% or so under these significant current densities. And the one most important and most challenging part is by maintaining these 2 very strict parameters, you have to run yourself for extended lifetime. In commercial water electrolyzers, minimum requirements, 10,000, 50,000 hours of continuous operation without changing the catalyst or membranes and so on. But here, as a very general requirement, more than 1,000 hours stability test is generally needed to make economic sense. So by listing out those very strict parameters to help us to deliver these cost targets, I want to emphasize is, of course, the foundations, everything relies on the development of the catalytic materials. But however, if we really want to deliver the performance, we sometimes also need to emphasize development of the electrolyzers, more practical electrolyzers, and test the catalytic materials in the electrolyte to see what's the real requirement and also what's the practical challenges that we need to solve with. So the coupling between the catalyst and reactor engineering will help us eventually to deliver the performance targets that we set. So that's coming back to the major two thrusts in my groups over the past 2 years or over the past several years or so, is we are developing novel catalytic materials to improve their intrinsic activity and selectivity towards CO2 reduction. And also at the same time, we are very interested in putting that materials into some of the novel electrochemical reactors that can help us to push up the current density, to push up selectivity as well as stability and so on, to make the catalytic development under a more practical environment, and to find out the more practical challenges that we have to solve. So in this talk, I would like to share with you some of the examples in both thrusts, catalytic materials design as well as the device engineering, to share with you why these two thrusts are equally important in the group. So first of all, catalytic materials design. So you know, my independent research, my group started about 2016 or so. At that time, we were taking a look at the CO2 reduction field, especially the CO2 reduction to CO. At that time, there were only very few selections of catalysts that can really drive high selectivity towards CO reduction, CO2 to CO reduction. Only some of the noble metals like gold and silver. And we were at the beginning, you know, thinking about if we can activate some of the earth-bound transition metals like cobalt, nickel, iron, and so on, because that has been widely investigated in a lot of the water splitting catalysts. So we were very naively thinking about if that can also be utilized in CO2 reduction. So at that time, very real studies has been focused on these transition metals. It's because two reasons. Number one is they were generally considered as very, very good HER catalyst. So you never want to start with a catalyst for CO2 reduction that has excellent HER competition activity, right? And number two, the second reason is even more serious, is because for those transition metals, you can imagine if there is any CO2 get reduced on the surface to produce CO, not only as a product, but also for some of the hydrocarbon generation, CO can serve as important intermediates. Those early transition metals, including nickel, cobalt, and iron, they can bind CO very strongly. So this is similar to, you know, the poisoning effect in human beings when we breathe in CO, that the iron species in our blood can bind CO very strongly. So the oxygen cannot exchange. This is the same thing happening on the surface of nickel. Once you have CO, that binding strength is too strong. So the site will be poisoned. So you cannot generate any CO2 reduction products. So at that time, we were thinking in a different way. We were thinking about how we can tune and change the electronic structure of the transition metals to make it possible to be a CO2 reduction catalyst. So at that time, we were thinking how if we can further shrink the size of the nanocrystals or nanoparticles of nickel all the way down to isolated transition metal single atomic site catalyst. So by saying here single atom catalyst is we referring not a floating atoms in the atmosphere or so. We are referring isolated transition metal atoms that is anchored in some well-defined, let's say, carbon substrate, but there is no direct nickel-nickel interaction. So the spacing between them is very large, so there is no metallic bond formed, so that you can significantly change the electronic properties. We were hoping that by changing the morphology could result in some of the electronic property change towards more CO2 reduction selectivity. So at that time, we collaborate with Professor Ian Snoskov. At that time, he was still at Stanford. And we start with some of the simulations to see if the nickel single atomic site can be selective or not. So we start with some of different coordination structures with or without nitrogen, you know, single vacancy, double vacancy, and so on. So look at each of the elementary steps and do the thermodynamic analysis of free energy for each of the elementary step. If we take a look at the nickel metal first, so as we can see, the CO2 activation actually is relatively simple on the nickel metal surface. However, once the CO forms, as you can see, there is a very deep thermodynamic sink that makes the CO desorption becomes very difficult. So it means that the catalyst is not active CO2 to CO reduction. But if we take a look at this single atomic site, even though the activation process for CO2 reduction is relatively higher than nickel metal surface, which of course can be offset by applying more negative potentials, but the CO2 desorption becomes much easier. So at that time, it gives us a lot of the strong confidence that these type of single atomic sites could be utilized for CO2 reduction. So my postdoc at that time, Dr. Kunjian, now associate professor in Shanghai Jiao Tong University, he started this journey. At the very beginning, we are not that experienced in controlling the atomic site of synthesis of the atomic site of single atom catalysts. We just mix a lot of these precursors together and do the thermal annealing. And as a result, we got this core shell structure. So that gives us a very hard time. It's because this core shell structure has a lot of different sites, structures inside. You have these nickel nanoparticles, you have the graphene share. In the graphene share, you might have some nickel dopants and so on. So where is the true active site? It's challenging at that time. We don't know whether this is nickel single atom or so. By using a lot of sophisticated characterization tools, because in this case, we cannot use the traditionally used X-ray absorption spectroscopy to differentiate nickel-nickel bond versus the nickel-nitrogen or nickel-carbon bond. The bonding distance is different, but because these nickel nanoparticles are always embedded in your materials and cannot be leached out, suggesting the very tight surrounding of these graphene shares. And eventually we utilize this atom probe tomography that can help us to provide us a very direct piece of evidence to show us that there is a lot of these isolated nickel dopants in the graphene share region. So suggesting that these could be the active site for CO2 reduction to CO. As we can see from the catalytic performance, the CO ferritic efficiency continues to ramp up to about 80 to 90% while suppressing the competing hydrogen evolution reaction towards only 10% or so. So this comes at the very first version of our journey. And then the second version, we were thinking about in a different way. We know that because the surface nickel dopants is the active site. If that's the case, we can just get rid of these nickel nanoparticles because they are not participating into the reaction. So why don't we start with graphene nanosheets while you can dig a lot of holes before you incorporate some of the nickel dopants inside and then do thermal annealing. Because of the very strong formation energy, you can automatically suck those nickel atoms into the defects and making those nicely isolated nickel single atomic site on the graphene nanosheet. And during which, by controlling the amount, you won't result in any of the particle or cluster formation, which can be easily detected by the X-ray absorption spectroscopy. So in this case, we further demonstrate the high performance of nickel single atomic site, while the selectivity over 90% has an even wider electrochemical window. And then the third version is we further simplify the synthesis by using the not only graphene oxides nanosheets, because in this case, we cannot get large quantities of catalysts per batch of synthesis. Now, let's see if we can translate the active site onto the carbon black substrate, which is of course, thousands of times cheaper than graphene. And we demonstrated to be also synthesizing these isolated sites on the carbon black, which is very cheap. And also now we can, in a large quantity per batch of synthesis, to synthesize those single atomic site catalysts. And the performance is even better. The selectivity performs a wider electrochemical windows. The interesting part in summarizing this continuous work is that if we normalize the CO2 reduction activity on the number of active sites in all of these three versions of catalysts, they have surprisingly similar turnover frequencies. So this is a very strong side evidence to show us that while their performance, their morphology and their apparent performance are different, but they all share the same active site, which is the nickel single atomic site. And also, once we get the capability of scaling up the materials production of single atom catalysts for CO2 reduction, the next step for us to think about scaling up this process is, of course, the current density. Because we know that in a lot of these traditional H-type cells, we are always limited by current density. Why? This is relevant to the mass transport issue. Because we know that in traditional H cell, our electrode is actually submerged in water, in electrolyte, and we saturated that electrolyte with CO2. So the CO2 molecule that you get reduced is actually in soluble phase. So think about that. Surrounding your electrode surface area is only a few less than 0.001% is CO2 molecules. Actually, 99.999% is water molecule. So in that case, of course, it's very easy for the HER to pick up. And also think about this mass diffusion limit. The bulk concentration of CO2 is only 1,000 to 2,000 ppms. So when you are reaching to a significant amount of current density to deplete the CO2, to generate the CO product, let's say, you will deplete the surface CO2. And then eventually the limitation will not be the kinetic limited step. It will eventually becomes the mass transport from the bulk CO2 towards the surface. That mass transport, how fast you can bring the CO2, it becomes the limitation. So that's always the reason why we observed this phenomenon. So in H cell reactors, we always test of the CO selectivity, ramp up to 90 or even 95% to a maximum. And then if you want to apply more and more negative potential to ramp up the current density further, right? You won't see the CO current density further ramped up. Actually, as a result, you will see the selectivity of CO starts to drop. As a result, your hydrogen starts to pick up because you run out of surface CO2. And there is a lot of water molecules. They can also pick up the electrons to generate hydrogen. So this will always limit your current density to about 10 to tens of milliamp per centimeter square. So that comes with the membrane electrode assembly reactor that has been widely observed in fuel cell studies, hydrogen fuel cells, where there is no liquid fuel. There is no liquid water involved. So in this case, you can pump in very high purity of CO2 gas. Of course, you can get some of the humidification. 5% of water vapor is enough. 95% of purity of CO2 gas coming in to the cathode. That will get reduced by your cathode catalyst generate the product you want. While at the same time you generate the OH groups, that will be transported across the anion exchange membrane. So this part, I will introduce this part later in my slides because this has been recently updated with which is not OH transport anymore, it's carbonate transport. I will show you a little bit more in the next few slides. But in this case, that OH crossover will get oxide, generate oxygen. So you completely flip over the concentration ratios between water and CO2. Before is 0 point several zeros of CO2%, right? Now you have 95% of CO2. Using the same single atom catalyst, exactly the same catalyst, but in each of these different reactors, now you see the complete different reactivity. In this case, saturated current of CO is only about 10 milliampere or so. But in this MEA reactor, we can ramp up to 100 to 200 milliampere per centimeter square while still maintaining more than 95% of CO selectivity. So in this case, it's 1 order of magnitude improvement compared to the H cell. And with the catalyst scaling up with the current density also can be scaled up. Now we can, do some of the initial tasks of scaling up by fabricating this 10 by 10, which is about 100 semi-square electrolyzer, spray coat with the catalyst using our MEA design. Now out of this 1 unit cell, we can generate 8 to 10 amp per unit cell of current. So now the current is in a complete different unit. This is amp right now. And out of this 1 unit cell, we generate about 3 to 4 liters per hour of CO production rate. Of course, if you want to further scale up the device, you can pack, it's like fuel cells, you can pack multiple devices, unit cells together to generate more CO. So I will skip these slides. A very quick sub-conclusion of the first part of my talk. I want to use this example to share with you some of the philosophy of our group's research. At the very beginning, we may deal with a very complicated structure of the catalyst. We don't know what's happening on the surface. By a lot of the detailed characterizations, as well as simulation understandings, we will identify the active site. By doing so, we can further simplify the structure of the catalyst and also further improve the productions of the catalyst in a lower cost productions also, and also putting that into more practical reactors to scale up the current densities as well as selectivity. Like what I mentioned, the reactor design is very important to the CO2 reduction field. This is true for the CO2 to CO generation. And this is even more important to the CO2 reduction to liquid fuels. Why we care about liquid fuels is because the CO2 reduction to gas products, CO ethylene, of course, is very valuable. Also, CO2 reduction to some liquids like formic acid, acetic acid is also very valuable, considering its very high energy densities, easy transportations, and the most important is very naturally separated from the CO2 stream. Because we know that in gas products, if you have excessive CO2, you have to do a downstream separation process to separate that CO2 and feed back to your reactor again. But for liquid products, there is no need for that part. And also a lot of these techno-economic analysis suggesting the very competitive cost of liquid fuels coming from CO2 reduction compared with the existing technology. However, I want to say here that this type of techno-economic analysis overlooked a very, very important factor that people recently noticed, which is the impurity issue, especially for liquid products. That is the liquid product in a mixture with liquid electrolyte. Because we know that in a lot of these traditional CO2 electrolyzers, liquid electrolyte is a must, which can provide two functionalities. Number one is the fast ion conduction. Of course, it separates the cathode and anode. The liquid electrolyte can become the very good conductors for the electrons, for the electricity to conduct through the electrolyzer, so that you have very low IR drops, ohmic loss, and so on. But the second function for CO2 reduction to liquid fuels for the liquid electrolyte is the product collection. So in this case, in the formic acid, once the CO2 get reduced to form the formate, it will be continuously flushed out by the liquid electrolyte. So in fact, you are not producing the product of formic acid. You are actually producing the formate ions that is in a mixture with liquid electrolyte. So you will always have to do a downstream product separation process to extract the high purity and high concentration of formic acid product to really compete with the traditional chemical engineering approach. It's because those approaches the costs are based on the final product of high purity and high concentration of liquid fuels. So in that case, if you think about that downstream separation process, you will add a huge chunk of separation cost to your previous analysis. That will make your process not economically attractive anymore. So that actually naturally becomes motivation for our project, is if we can do some kind of reactor engineering to help us to directly get high purity and high concentration of formic acid without the need of downstream separation process, that could help us to eliminate this huge cost. So here comes the very first version of our group's design of porous solid electrolyte reactor. So instead of using the liquid electrolyte, now we want to separate the two functions, ion conduction and product collection, using this solid electrolyte device. So instead of using the liquid electrolyte, now we can use the high porosity polymer ion conductors. We can also call them solid electrolytes to separate the cathode and anode. So this can actually separate the liquid, that can also help us to separate the fast ion conductions, which can still be well maintained by this solid electrolyte between cathode and anode. At the same time, the solid electrolyte won't get soluble into the water. So once you have the deionized water stream that is flowing through the pores of the solid electrolyte layer, the generated liquid fuels can be continuously collected by the DI water. So in that case, you don't have any potassium ions, sodium ions, bicarbonate ions in your downstream formic acid solutions. And in this case, as you can see from the CO2 reduction get reduced on a form a selective catalyst, forming this formate, cross over the anion exchange membrane into the middle layer of solid electrolyte. At the same time, water get oxidized, or hydrogen, whatever the reactant that you want, will release the protons that is coming through this cation exchange membrane into the middle layer of solid electrolyte. So these formate and proton will met together and recombine together to form the pure formic acid molecules that can be flushed out by the DI water to get high purity of liquid fuels. To demonstrate this concept, at the very beginning, we synthesized this two-dimensional bismuth catalyst, which is very selective to formate. This can be seen from a traditional H-cell type test that within tens of milliamps, we can get over 90% of formate selectivity. Only trace amount of hydrogen and CO can be detected. So this high selectivity can be successfully translated into this solid electrolyte device. So this is the very first, the photo copy of the very first version of solid electrolyte reactor, where the middle plate is the solid electrolyte layer, cathode and anode, both sides. As you can see here, depending on different type of solid ion conductors, your IV curve could be slightly different. Of course, protons are easier to conduct, but both of them can reach very high current densities. And the most important thing is, while you're producing this high purity of liquid product, you can still maintain the high selectivity of formic acid, over 85% or so. And we know that if we're maintaining, let me make sure my time is still, we still have a few more minutes, okay. So let me focus on this a little bit more. So think about if we're maintaining the production rate of formic acid by holding the current density. Now let's tune down the DI water flow rate to flush out the product. You can effectively accumulate more and more formic acid solutions. So as you can see here, with slower and slower DI water flow, the maximum concentration of formic acid that we can accumulate in that work is about 38%. That is about 6 to 7 moles per liter. And also, if you have continued to produce about 0.1 moles of pure formic acid solutions, that stability can be run for hundreds of hours. So in this case, we demonstrate 100 hours, but now we have a new target of holding the current density to about 200 milliamp per centimeter and stably run for 1,000 hours. So we know that by accumulating more and more these formic acid solutions, you will sacrifice the product selectivity. So this is a trade-off. Your Faradic efficiency continue to decrease to about only 30% or so if you want to accumulate 38% of formic acid solutions. So this is natural. It's because you have the middle layer has very highly concentrated formic acid, and CO2 reduction is reversible, right? You have a high concentration product that will backlash your forward reactions. So that's number one reason. Number two reason is the middle layer formic acid will cross over to the anode and get oxidized. So your apparent selectivity of formic acid will be low. So in that case, we were thinking about how we can change the DI water flow to inert gas flow so that we can continue to flush the middle layer to bring out the formic acid vapor as fast as possible to avoid any accumulations. But at the same time, because you have a lot of these nitrogen gas, if that goes through a cold condensation process, the nitrogen gas can be separated easily, but the flushing out formic acid vapors can be condensed to become very high concentration products. So in that case, we were able to generate much higher concentrations, 10 to 15 moles per liter compared to the previous test. And also, if we push to the limit, we only flow in dry nitrogen gas, we can even get almost 100% of formic acid. But of course, this is not sustainable. It's because if there is no water in the system, the membrane and ion conductors will eventually die. The stability is a big issue. But we want to just to push the limit to see how high the concentration we can get. Of course, this solid electrolyte device design can be adapted to many different types of electrochemical synthesis. If you change the catalyst to acetate selective catalyst, you can generate high purity of acetic acid. Let me skip this. If you want to generate hydrogen peroxide from oxygen reduction, which is different from CO2 reduction, but they share almost the same mechanisms that you can use the solid electrolyte device to generate high purity of hydrogen peroxide solutions. I think my time is almost there, but one last slide that I want to share is the carbon loss issue that we recently discovered. So as you can see here, this is the MEA device that we demonstrated before. I noticed that the OH is the ion conductions, but in fact, when you do CO2 reduction on the MEA device, you generate those OH groups, which is a very high local pH, or pushing up very high local pH. Those OH groups will automatically react and absorb the CO2 molecules that is unreacted in your gas stream to form carbonate that will cross over the membrane and then get re-acidified by the OER catalyst because you generate a lot of protons at the OER side. That will have your CO2 moving from your cathode side towards your anode side. But the challenging part is that will come out together with oxygen, because if CO2 mixed with oxygen, then you cannot reuse that anymore. It's because you cannot directly refeed it back to the CO2 reactor. But you can do some downstream gas separation process. I don't have the time to go to the details of that, but I want to share with you that one potential mitigation methods is to have this solid electrolyte buffer layer where you can allow the carbonate to cross over, no problem, but block that from continue to travel into the anode. So you have this solid electrolyte layer that can have the protons generated from anode come to the middle layer to neutralize that crossover carbonate and generate high purity of CO2 gas again. So that can be recycled back to your cathode for the continuous utilization. So out of that demonstration, we can have more than 90% of conversion ratio of one pass conversion efficiency. So 100 CO2 molecule in, we can convert 90 of them, and only 10 CO2 molecules remained. Okay, so without further delay, I would like to conclude my talk. I hope that I convinced you guys that, of course, the catalytic material design is the foundation of the whole field. And also we have to pay a little bit more attention on the device engineering part that can also help us to continue to push forward the development of the field. That applies to not only the carbon research that my group has been focusing on, also oxygen, hydrogen, and nitrogen, that in the future, if we have further opportunities, we'll share with you guys. With that, I would like to thank my talented group, funding agencies, and I would like to take questions that you have. Thank you.
Thank you, Professor Wang, for your this wonderful talk. So now we have time for a few questions. So any questions from the audience?
Maybe I ask a question.
Okay.
The audience very quiet today. Right, Professor Wang, and thank you very much for your enlightening talk. Wow, I can see your group had a lot of experience in this CO2 reduction, and now extended to some other area as well. So when you mentioned about this MEA this membrane electroassembly for the CO2 reduction. It is that they always have this cover problem, right?
The crossover problem.
Yeah. So so that will make the stability of the device actually cannot last for a long time. So how will you deal with this kind of problem?
So, well, that's a great question. I think that's two levels of challenges here. So, of course, crossover, you will have a lot of carbon loss. That's what I do. So that's different. And also crossover could, introduce some of the instability of the membrane, because we know that a lot of the anion exchange membranes, especially for the hydrogen fuel cells, alkaline fuel cells, they don't like CO2, right? If you have some CO2, that could have some carbonate that could stuck inside of the membrane for the ion conduction instability. But there are a lot of new companies recently developed, different ion conductors for specifically designed for carbonate. So the stability issue for the carbonate crossover has been significantly mitigated. Some of the recent work, they demonstrate about 2,000 hours, 1,000 to 2,000 hours continuous operation for CO2 reduction. So I don't think the crossover in some specific design membrane is a big challenge.
Right, thank you.
But in generally speaking, the alkaline membranes is not as stable, lasting long as compared to Nafion in the PEM cells and so on. But there was a lot of progress is going right now.
So basically, if there's a better membrane, it could solve the problem.
Yes. So this is not on the catalyst design
right, exactly,
or the electrolyzer design level, but it's really a lot of these high molecule polymer engineering and so on. The a lot of ongoing efforts inside of that. Yeah.
Thank you.
Okay, we still have time for one short question. Any question from the audience?
Hi, Haotian.
Hello.
Yes.
Hi, this is Bolong. I have some question, short question for you. Regarding the MEA, can you give some promising expectations about futures? Because for synthesis, nanomaterials, usually, traditionally we do the tri-electro test, right?
Mm.
So in the future, can more and more people doing MEA test?
Yes, that's pretty sure. Of course, 3 electrode system test is always the foundation of the research field. Even for a lot of these research papers that has MEA test, they will always test their catalyst as a standard procedures to evaluate their intrinsic activity for their catalyst. But I do see more and more groups are using this MEA device to test their not only gas product, but also liquid product and so on. This is definitely a more practical reactor compared to H cell and even compared to flow cell. But of course, like, Lanshu just also mentioned, there is still challenges regarding the membrane stability. Also, there are challenges for the carbon crossover that we recently published that paper to specifically address that, but we know that this is not only solutions to address that, there will be many more solutions coming out. So there are still issues. Stability is a big issue, but also, the one-pass efficiency. So let's say you have CO2 stream coming in. If your conversion is only 10%, how you can continue to convert that 90%? So that is relevant to your crossover of carbon loss, as well as if you slow down your CO2 flow in, if you reach to 80% of conversion, how you can maintain that high selectivity. So there are still some practical issues when testing in MEA studies.
Okay, thanks, Haotian. Thanks, Haotian, because as you said, this is true because of many practical issues and problems when packaging in MEA devices.
Exactly. Yeah.
Okay. Thank you. And thanks very much for your perfect talk.
Okay, thank you. Haotian, I have a short question. Sorry to keep you so long. And as we know, the solid electrolyte normally has a lower conductivity, ionic conductivity, as compared to the liquid one. So, but I noticed that in your cell using the solid electrolyte, you still have a very high current density. So, is there any, or what is the minimum requirement on the ionic conductivity for the solid electrolyte?
So solid electrolyte, even for the polymer ion conductors like the sulfonate groups that widely used in Nafion membranes, right? So the estimation of the conductivity is only around 0.02 to 0.01 to 0.02 Siemens per centimeter. So if you're considering liquid electrolyte, still liquid electrolyte, if you have salts inside of the liquid electrolyte, they're still, the ions mobility is much faster. So, but the thing is, for solid electrolyte, what we can do is we can really narrow down the distance.
Okay.
That's the reason why MEA stands out compared to traditional flow cells, right? Because you can press the two electrodes very, very short, tens of micrometers. So even though your resistivity is slightly higher, but your eventually IR drop will be much lower. So the solid electrolyte in our case is about 3 millimeters in thickness. This is still considered very thick for commercial, for industrial relevant current densities, especially if you're running 500 to 1 amp. 500 milliamp to 1 amp per centimeter square, because you think about the resistance for these 3 millimeter thickness is about 1 to 2 ohms. So even for that, that's too high. So we are thinking about how we can further thinning the thickness and also further increase the ion conductivities. But that's the state of the art, because we are not polymer guys. We don't have other tools.
Okay.
Further improve the ion conductivity. Yeah.
Okay. Thank you very much. So with that, we finished the first session of this morning. So thank the two speakers once again. So now we'll have a short break, and the second session will start